Hello students, welcome to Technogate and welcome to the subject on control systems. In the previous session we have discussed about Nyquist plots. In this session we are going to start with the last topic of control system, that is state space analysis. Okay, so far whatever the techniques which we have discussed, whether it may be RH criteria or root locus or Bode plot or polar or Nyquist, all these topics are based on one tool, mathematical tool, that is nothing but transfer function. And we know that the limitations of transfer function, that the transfer function is analysis is applicable only to LTI systems, linear time invariant systems. But whereas if I am giving a non-linear or time varying systems, in that case I cannot able to apply transfer function analysis. The second limitation of transfer function is the transfer function analysis is not applicable if the initial conditions of the system is not equal to 0. That means if I am having a initial energy stored in the inductor or initial energy stored in the capacitor, in that case I cannot able to apply the transfer function analysis. Next, third one, the other limitation of transfer function is it is best suitable for SISO system. That doesn't mean that we cannot able to apply the transfer function analysis to MIMO systems. Even we can apply the transfer function analysis to multi-input, multi-output, but it is a time consuming. So that means if I am having a system which is having more than one input and more than one output, in that case the other transfer function analysis is not that much suggestible. So to overcome all these limitations, we are going to enter into a modern control theory, that is nothing but state space analysis. So the state space analysis is a modern control theory where we can able to overcome all the limitations of transfer function. Since all the techniques which we have discussed like RH criteria, root locus, Bode, polar and Nyquist, they are also running behind the principle of transfer function. Whatever the limitations of transfer function even are applicable to these particular techniques. That means even RH criteria, Bode, polar, Nyquist and all those stuff are also not applicable for non-linear as well as time varying. They are also not applicable if the initial conditions are not equal to 0. Are you following? So to overcome those things, we are going with the state space analysis. That means, can you tell me now what are the advantages of state space analysis? The advantages of state space analysis is the state space analysis can be applicable for all kind of dynamical systems. Applicable for all kind of dynamical systems. That means I can able to apply for linear systems, I can able to apply for non-linear systems, I can able to apply for time varying systems, I can able to apply for time invariant systems. For all kind of dynamical systems, I can able to apply state space analysis. Next one, the state space analysis is also applicable if initial conditions are not equal to 0. Even though initial conditions are not equal to 0, still we can able to apply state space analysis. The next one is, okay, so the state space analysis is applicable for both SISO as well as MIMO systems. SISO means single input, single output systems, as well as MIMO means multi-input, multi-output systems. We can comfortably apply to all kind of dynamical systems. SISO or MIMO or linear or non-linear or time varying or time invariant systems. Right. Next, if you take or consider a transfer function analysis, transfer function analysis will give you, for suppose if I am taking this is my transfer function of a particular system, and if I give some input, I can able to obtain the output. But that means I can able to see the behavior of this system. Okay, so I can able to determine the overall behavior of the system. That means I can able to take the ratio of overall output to overall input, and from here I can able to make a comment on stability, whether the overall system is stable or unstable. But there are some situations where, for suppose if I am taking, this is my system, okay, here I have a component 1 and here I am having a component 2 and here I am having one more component 3, and these components are connected to the summing point, and this is my overall output C of S and this is my input. Right now, if what we are going to do in transfer function is we are trying to determine the overall transfer function and we are trying to say whether it is stable or unstable. That means I can able to obtain the overall behavior of the system with the help of transfer function. But there are some systems where the overall system is stable, but if you try to see the internal components may be unstable in nature. Okay, So the internal component may be unstable, but the overall system is stable. Or all the internal components are stable, even though all internal components are stable, but the overall system may be unstable. There are different cases, possible cases you will find, right? So the point is, with the help of transfer function, I cannot able to identify the internal behavior of the system. But whereas the state space analysis is used to analyze both internally as well as overall behavior. So the state space analysis is used to get the information of both internal behavior as well as overall behavior. So both internal and overall behavior can be able to identified. Okay, both internal behavior as well as overall behavior of the system can be able to understand with the help of state space analysis. So because of all these advantages into consideration, generally once if you enter into higher education, MTech, or if you are taking a PG courses, we are going to start with this topic only. Okay, so in undergraduation level we are not going in depth into the state space analysis, but the moment if you are going enter into a specialization, a particular specialization of control systems and control, or control and computing, whatever may be the higher education specialization which you are choosing in IITs or NITs, then the first topic what you are going to study in those specializations are state space analysis. Okay, we are going to do the analysis in state space analysis. Okay, and after that we are going to apply to nonlinear techniques, whatever may be the different techniques which we are going to study in higher education. Okay, so in GATE exam previously, okay, 5 to 7 years back, you will have highest importance for this state space. But from last 3 to 4 years or 5 years, you are getting only 1 or 2 marks. Okay, so that is the reason, even though it is a very vast topic, okay, let us try to restrict our analysis to some limited period of time. Okay, so the state space analysis is called modern control theory, and you will have so many advantages. And again, the state space analysis is used to make a comment on the performance of the system, like stability, speed as well as accuracy, but with added advantages of different systems. Are you following? Right. Now let us try to see how to represent a given system in state space. How to represent a given system in state space. First let us try to understand, okay, what is the meaning of state. The meaning of state is, it is used to represent the behavior of a system. Okay, state is nothing but the behavior of the system can be analyzed with the help of this state. That means, for suppose if I am taking a simple RLC circuit, assume that this is input to the system Vi of t, and the elements are R, L, C, and assume that the current through this particular circuit is I of t. Okay, now if you want to analyze the behavior of this system, for suppose if I know the current through the inductor for all the time as well as voltage across the capacitor for all the time, then I can able to completely understand the behavior. Rather than knowing this, for suppose if I know the initial initial current in the inductor and initial voltage across the capacitor, with this I can able to derive IL of t and Vc of t. In network theory we have seen DC transients where we have seen standard formulas for calculating current through the inductor and voltage across capacitors, right? So in the same way, if I know the current through the inductor and voltage across capacitor, then with the knowledge of this current through the inductor and voltage across capacitor as well as the knowledge of the input, I can able to understand the complete behavior of this circuit. Complete behavior means at what time? At time t equal to some 4 seconds, what is the energy stored in the inductor? How much energy that is stored in the capacitor? How much energy is dissipated in the resistor? So we can able to get the complete information, complete idea about this electrical circuit, provided if I know the knowledge about what kind of variables, knowledge about input as well as knowledge about the current through inductor and voltage across capacitor. So these variables which are used to decide the behavior of the complete system are called as state variables. So what is the definition of state variables? The variables which are used to decide the complete behavior of system are called as state variables. So I am again repeating the definition of state variables. The variables which are used to decide the complete behavior of overall system are called as state variables. Now here if you are taking electrical circuit, for electrical circuit in general, default for electrical circuit, always for inductor, we are going to use current through the inductor. Okay, we are going to use current as a state variable, whereas for capacitor, we are going to choose voltage across the capacitor as a state variable. Okay, so always for inductor, current through the inductor is chosen as state variable. For capacitor, voltage across capacitor are chosen as state variables. State variables. Are you following what I am saying? Right. Once if you understand this point, now let us try to understand how to identify the number of state variables. Here how many state variables are there? 2 state variables. So that means, can I say the number of state variables? From now onwards I will use SV to represent state variables. In short notation we can say SVs. The number of state variables for a given electrical network is equal to what? Can I say number of independent energy storage elements? How many energy storage elements are you finding in this electrical network? I can say 2 energy storage elements. One is inductor and another one is capacitor. So that's it. I can say the number of independent energy storage elements. Number of independent energy storage elements. Energy storage elements. Now what is the meaning of this term independent? The meaning of the term independent is nothing but, for suppose if I am having one more inductor which is connected in series, then in that inductor also can I say the same current is flowing? At that case, can I say those 2 inductors I can treat it as only one energy storage element. Similarly, for suppose if I am having one more capacitor which is connected in parallel across this. In that case, if the capacitor, one more capacitor is parallel across this existing capacitor, the voltage across those 2 capacitors are remain same. In that case, those 2 capacitor combination I can treat it as a single energy storage element. So that means here the term independent means after removing the series combination of inductors and parallel combination of capacitors, the effective number of inductors and capacitors you have to calculate. That is the reason I am using the term independent energy storage elements. Okay, so the number of state variables for a given electrical network will be equal to number of independent energy storage elements. Now relax. Let us try to calculate the KVL equation of this electrical network. Okay, so if I try to write the KVL equation, so what you are going to get, assume this is plus minus. So if I start or move from here, minus Vi of t plus R into I of t plus L di of t by dt. Okay, right, or I can write specifically IL of t, because the current through this circuit is nothing but current through the inductor, because it is a series RLC network. Since it is a series RLC network, the current in the entire circuit will be remain same. So if I am saying I of t, the same current will pass through the inductor. So that is the reason I am writing dIL of t by dt plus 1 by C into integral IL of t dt, because KVL equation I have to write, voltage across capacitor equation I have to write, right? Now if you try to remodify this equation, okay, what you are going to get? So what you are going to get, so if you take R into IL of t plus L dIL of t by dt plus 1 by C into integral IL of t dt equal to Vi of t, equal to Vi of t. Are you following what I am saying? Now if you try to see here, so let me try to take the derivative of this expression, then you are going to get what is the order of this differential equation you will get. I can say the order of the differential equation is second order, or else other way of approaching, so you may get confused with this equation. Now what I will do is I will try to determine the transfer function. If I try to determine the transfer function of this one by taking voltage across capacitor as output variable, so what you are going to get, I can say Vi of S divided by, Vi of S or V naught of S, voltage across capacitor, Vc of S divided by Va of S. If I do that procedure, what you will get, 1 by Cs divided by R plus Ls plus 1 by Cs. Yes or no? Right? Now if I do the simplification, what you are going to get, guys, 1 by LCS square plus RCS plus 1. Am I correct? Now if you understand here, the transfer function I am getting this formula for the same electrical network. For the electrical network, number of state variables are number of independent energy storage elements. Whereas if I got the transfer function, what is the order of the transfer function you got? Second order. That means if I am not giving an electrical network and if I am giving the corresponding transfer function, and ask you to determine the number of state variables. How to determine the number of state variables? Simply order of the transfer function or order of the denominator polynomial. So what is the next statement? The number of state variables for a given transfer function is equal to order of transfer function is equal to order of transfer function. This is the second point you have to remember, right? Now what I will do is I will do the cross multiplication. If I do the cross multiplication, what you will get 1 into Vi of t, and after that you will get LC s square into Vc of t plus RC into s into Vc of t, right? Not Vc of t, this is Vc of s because it is in s domain. So this is also Vi of s, right? Plus 1 into Vc of s. What I have done is I have done the cross multiplication. Now take the inverse Laplace transform of this. If you take the inverse Laplace transform, what you will get? Vi of t equal to LC into this I can write as d square Vc of t by dt square. Then if you apply Laplace transform, you will get this expression, right? Plus RC into d Vc of t by dt, yes, plus 1 into Vc of t. Now if you observe, what is the order of this differential equation? Can I say second order? That means rather than giving an electrical network or rather than giving transfer function, if I am giving a differential equation and ask you to identify the number of state variables, can I say number of state variables for a given differential equation equal to order of differential equation. So the third point you have to remember is number of state variables for a given differential equation dE is equal to order of differential equation. So I hope you understand the definition of state variables and how to identify the number of state variables. Now let us try to see how to represent this network in state space representation. Right. Now let us try to see how to represent a system in state space representation. Now if I am taking some MIMO system, assume that I have a multi-input, multi-output system. This is my multi-input, multi-output system. Assume it is a linear system initially, and assume that this system consists of some inputs, okay, and so on. You will have some inputs, and for each and every input the system will produce a corresponding output, and we know that we are having n number of outputs, whatever it may be. There are huge number of outputs, because if you are taking a vehicle direction of the vehicle is treated as one output, okay, and the temperature inside the vehicle is treated as another output, and the speed of the vehicle we can consider as another output, and the traction control or cruise control is considered as another output. So there are n number of outputs will be there for a given system. So these are my inputs, and for each and every input the corresponding system will produce a corresponding output, okay. And assume that this particular system consists of storage elements, energy storage elements. The moment if the system consists of energy storage elements, those storage elements will be represented with state variables, okay. So assume I am going to represent that with some state variables. Now from now onwards I am going to use U symbol to represent input, and C symbol to represent output, and X symbol to represent state variable, okay, or Y symbol, whatever it may be, Y symbol. Let us assume I am going to represent with U1, U2, U3 and so on. I am assuming there are P inputs are there, and system is going to produce the corresponding output Y1, Y2, Y3 and so on. Let us assume there are Q outputs. How many inputs? P inputs are there, and how many outputs? Q outputs are there. And this particular system consists of some n energy storage elements. So those storage elements will be represented with state variables. So I can say these are n state variables. N state variables. Are you following? Right. So this is my MIMO system. Now if I want to represent this MIMO system, which consists of P inputs and which is producing Q outputs with n energy storage elements or n state variables, I have to write two equations. Out of those two equations, one equation is used to represent the internal behavior of these states, and one more equation is used to represent the overall behavior or the output behavior of the system. One is used to represent the internal behavior of these states, another one is used to represent the output behavior, okay. So that is the reason those two equations are called as, one is to represent the state behavior, that is the reason we are going to call it as state equation, whereas the other is used to represent the output behavior, that is the reason we can call it as output equation, okay. We can call it as output equation. Are you following what I am saying? Are you following? Right. So now before that, let us try to write the matrix form, okay. So if you are taking input vector or input vector, because the input consists of some magnitude as well as direction. I am using the term vector. So input vector I can represent with u bar of t, and what is the dimension of this input vector? u1, u2 and so on. Matrix dimension is how many rows are there? P rows. How many column is there? 1 column. So the dimension of input vector is u bar of t, and the dimension of output vector, let us try to calculate how many outputs are there. Output vector I can represent with y bar of t. So you are going to get y1, y2 and so on. Q outputs are there, so the dimension is q by 1. And similarly, how many state variables we have assumed? N state variables. So if you combine all those state variables, whatever the vector which we are getting is called state vector. I can represent with x bar of t. So you are going to get x1, x2 and so on, xn. So what is the dimension of the state vector? N by 1. Okay. So I have state input vector, output vector, state vector. Right. Now if you try to write the equations, y1 output equation, y is produced because of u1. If I give u1, you will get corresponding output y1. Because of u2 also, you will get a different output y1. Because of u3, you will get a different output. Because of up, you will get a different output. Right. Next. Again, I can say that this output is not only depend upon these inputs, even it depends upon the energy storage elements also, right? So the output produced from a system depends upon two parameters. One is input, second one as well as the states. Next point. Next, here generally what we are doing is in state equation, directly I will give, because if I am going in depth into this concept, because it is a very vast syllabus. So if I am going in depth, you may get confused. Anyway, you are going to study in upcoming higher education sectors. Okay, here I am going to teach the knowledge which is required to solve the questions in the GATE exam. Okay, so the general standard format of state equation is the first order derivative of state vector, which is expressed in terms of state vector as well as input vector, which is expressed in terms of state vector as well as input vector. What is x bar dot of t? X bar dot of t is nothing but dx bar of t by dt, which is nothing but first order derivative of state vector. First order derivative of state vector, which is expressed in terms of what? State vector and input vector with some coefficients. Those coefficients combinedly we can call it as a bar vector and b bar matrix. Okay, a bar matrix and b bar matrix. Similarly, output equation is nothing but the output vector is represented in terms of inputs as well as in terms of state variables. So the output vector y bar of t is equal to c bar into x bar of t plus d bar into u bar of t. C bar into x bar of t plus d bar into u bar of t. Are you following? Right? So combinedly these two equations we can call it as the state space representation of any system. Combinedly we can call it as the state space representation of any system. That means if I am giving some electrical network and ask you to represent in state space representation, then how many equations you have to write? Two equations. What are those two equations? One is state equation, second one is output equation. What is state equation? Derivative of state vector in terms of state vector and input vector. What is output equation? Output in terms of states and input. Okay, now let us try to see the dimensions of all those matrices, A bar matrix, B bar matrix and all those stuff. Okay, so now we know that what is the dimension of x bar of t. Since we have assumed n state variables, this is n by 1, u bar of t p by 1, right, and u bar of t here p by 1, and here x bar of t n by 1 and output y bar of t q by 1, right. Now if I know the dimension of x bar of t is equal to n by 1, can I say the dimension of even x bar dot of t also n by 1? Because ultimately I need to only take the derivative of inside elements, but the matrix dimension will not change. That is the reason here also how much you will get? N by 1. Now my question is, what are the dimensions of A bar, B bar, C bar and D bar? This is first and foremost important step while representing any system in state space representation. Can you tell me what is the dimension of A bar? A bar dimension is obtained by simply see here. Here there are, according to matrix multiplication principle, okay, the number of columns in the first matrix should be equal to number of rows. That means I am going to get number of columns n, here also number of columns p, here also number of columns n, here also number of columns p, right. So I got the information of number of columns. Now I need to get the information of number of rows. Now if I multiply these two things and if I multiply these two things and add these two matrices, I need to get resultant n by 1, because if I want to equate two matrices, the dimension must be same. If I want to get the same dimension, here how many rows are there? N. The same rows you will get here also. Then if you cross check n by n into n by 1, you will get n by 1. N by p into p by 1, you will get n by 1. Right? Here how many rows are there? Q. Keep the same rows here, q and q. So now if you multiply q by n into n by 1, you will get q by 1. Q by p into p by 1, you will get q by 1. So you are going to equate or compare the two matrices. So these dimensions of the matrices are very important. So here A equal to having n by n is called as input matrix, or specifically not input, state matrix. We can say it is called state matrix, or we can call it as even also system matrix. We can also call it as system matrix. And if you observe clearly here, n by n, number of rows are exactly equal to number of columns. That is the reason always state matrix or system matrix is a square matrix you will get. It is a square matrix, because we know that if number of rows are equal to number of columns, that matrix is called a square matrix. And B bar, what is the dimension of B bar? B bar is n by p, and this is called as input matrix. We can call it as input matrix. And what is C bar? C bar is q by n, is called as output matrix. We can call it as output matrix. C bar is called output. The last one is D bar. D bar is equal to q by p. It is called state transition matrix or direct transition matrix. We can call it as direct transition matrix. We will understand what is the meaning of direct transition or state transition matrix. Direct transition matrix. Okay. So the first and foremost important step is you need to identify the dimensions of the matrix. So whenever if I am giving a system, it may be electrical system or differential equation or transfer function, the first step is identify the number of state variables, and after that write the state equation and output equation in terms of the standard formats. Okay. So whenever if I am asking you to represent in state space, you need to represent in this fashion. The first order derivative of state variables expressed in terms of states and inputs, and output will be expressed in terms of states and inputs. But here the dimensions of A bar, B bar, C bar and D bar you have to understand. Okay. Now let us try to apply this concept to some electrical network, how to represent a electrical network in state space representation.